Okay, welcome to the second half of 6.3a, the definite integral. If you haven't seen the first half, you can see there's lots of notations and example problems and more notations that we've gone through. And we are really all the way up to example 3, so we will pick it up from there. The average value, when we see average value, that is screaming the y value. If they talk about value of a function, that is the y, that is the f of x, that is the height, and we want the average. And Mr. Hartz gave a really good analogy of what's going on this when he talked to me about, let's say we've got a function looks something like this, and we're looking for the average height from, say, A to B. Well, the integral gives us that area under the curve, and that area under the curve on the integral, when we do things like integrate f of x from, let's say, a to b dx, the f is the y value, the dx is the x value. Integral means we use all the dx's that we can fit from a to b. In theory, we're using an infinity of those. So by the time we integrate, we've gone from here to here times all of our heights. Well, if I divide out the x, the length of x, I'm now left with just all of the heights, the average height there. And Mr. Hartz's analogy was, let's say that this was built out of an ice sculpture. When this thing melts, it would melt to the average height. So whatever's down here would be canceled off by whatever's up there, and we'd just be melted there. So there's our average value. So what we want to do then, to find that average value, is we want to find the integral of x squared minus 1, in this case from 0 to root 3 dx, the y's times the x's, all of them. And then we're going to find, so we're going to find the integral, and then we're going to find the average height. All right, so that would be, well, to get to an x squared antiderivative, I need an x cubed. That gives me 3x squared, but I don't want 3, so cancel it. Antiderivative minus 1 is minus x, and we're doing this from 0 to root 3. So we get root 3 to the third on 3 minus root 3, all minus 0 to the third on 3 minus 0. So here we have root 3 to the third, that's root 3 times another root 3. And we end up with 0. Now, that's not such a great example problem. So what this tells us is on this curve, x squared minus 1 looks something like this. From 0 to root 3, somewhere right in here, there is just as much curve, or just as much area above as there is below it. But I'm going to continue that. This is the integral value. So in theory, here's what we would do. Our average value would be 0 divided by b minus a, or root 3 minus 0. It would be 0 on root 3, and that would be it, but of course that's 0. So that shows the process. Again, maybe not the best example, but kind of interesting that we did have the square root of 3 gave us just as much area above as below. Okay, so let's take a look at this problem. Here's something we have to be really careful with. Graph the function over the interval. Integrate the function over the interval, and then find the area. Well, when I integrate the function, aren't I finding the area? Oftentimes, yes, not necessarily. We could do this calculator. I'm just going to make a quick t-chart here. xy from 0 to 3. Put in 0, get out 0, 0, 8. Put in 1, get out 1 squared, 1 plus 8, 9, minus 6, 3. Put in 2, get out 4 plus 8, 12, minus 12, 0, and put in 3, 9 plus 8, 17, minus 18, negative 1. So big graphs, don't cheat yourself, you got lots of room here. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So we got a point at 0, 8, we've got a point at 1, 3, we got a point at 2, 0, we got a point at 3. -1, and we've got a curve, and we see that our curve crosses the x-axis, and maybe that tips us off to what the problem is here. We're finding the area bound in here, and in there. If I call this area 1 and this area 2, then our total area is area 1 plus area 2. But the integral will interpret this portion of the area as a negative. And we don't want to interpret it that way. That's the challenge. But the first thing we're supposed to do is find the integral. We're great at that. Integral from 0 to 3 of x squared minus 6x plus 8 dx. Yes, the parentheses matter. This is the y part. This is the x part of our rectangles in theory that we're building infinity of them. So if I ended with x squared, I must have started with x cubed, but the derivative of that is 3x squared. I want to cancel 3. If I ended with an x, I must have started with an x squared, but the derivative of that is 2x. I want -6, so times -3. There's -6. If I ended with 8, I started with 8x, and I'm doing this from 0 to 3. I put in 3, and I get 27 on 3 minus 3 times 9 plus 24 minus 0 plus 0, and I put 0 in there. So I get 9 minus 27 plus 24, or 36 minus 33, excuse me, minus 27. I get 6. That's the integral value. But it's important to understand 6 is equal to A1, that area, minus A2. This area, where the areas are said to be positive. And we don't want that. We want area 1 plus area 2. And to find that, there's an easy way with calculator, but by hand, we have to integrate from here to here, from 0 to 2, and we have to integrate from here to here. And what we really want is the integral of f of x dx from 0 to 2 minus the integral from 2 to 3 of f of x dx, because, or we could say plus the absolute value of, because this is going to be interpreted as a negative value. Now, there are ways to shortcut this right now, but this would be the process that we need to go through. So we're going to go ahead and go through it. The good news is we know that the integral of f of x dx is x cubed on 3 minus 3x squared plus 8x. It would be plus c, but we have definite integrals here. So from 0 to 2, if I go 0 to 2 on this first, I get 8 on 3 minus 3 times 2 squared minus 12 plus 8 times 2, 16 minus zeros for all of those. From that, I need to subtract the integral from 2 to 3. So put in 2 again, and I get 8/3 minus 12 plus 16. We've done that. We're going from 2 now to 3. Oh, I should have put in 3 first, excuse me. Minus, so sorry. This would be the integral, the value at 3 we get is the same value we got up here at 3. 6. We get 6 minus, now put in 2, 8/3 minus 12 plus 16. And when we get done with that, I'm going to leave that to you in the calculator. It'll give me an opportunity to show you what's going on. Another option for us here would be, let's go back up here, dim this a little bit. Notice if I take this function and put it in there as absolute value, what that really does to our graph, the graph of the absolute value, you can check this in your calculator, would look a lot like that, except as we came down here, this part would bounce up over the top, and now we'd have 2 positive areas. And we'd get this part up here with A1. And we end up with what appears to maybe be 7 1/3. Now, it would be wrong to say that 7 1/3 from our calculator approximation. We should just say it's 7.333. But I would suspect if you go through this process by hand, you would get 7 1/3. But you can double check as our home viewer. So here's a look at your homework. And good luck. Come in, make sure you're coming in, ask questions, and thanks to Mr. Hartz for his melting ice analogy. I will use that forevermore.